Hi guys, you're welcome to this session. This is the fourth session in our reinforcement learning series. So in today's session, we are going to be looking at another important aspect of reinforcement learning. So today, what we are going to be looking at is the mathematics behind learning itself. So I'm going to call this the mathematics behind learning. Now, the core idea behind this is since we only need three equations to understand, very much the algorithm, from reinforcement learning to PPU. I've said it that this series is going to start from the basics of reinforcement learning, like we have always done, up onto PPO, which is principal policy optimization, which is used in advanced algorithms like LLMs, training of LLMs, fine tuning. That's post training, fine tuning, and so on. Or maybe RLHF, that's reinforcement learning with human feedback and all of that. So these are things that are being used in those areas. So this is what we are seeking to cover, and there are three equations that are very central to this. Now, to understand, these three equations, we are going to look at the first one of them. The first equation is the discounted return. Okay, equation one is the discounted. So for this equation, we've briefly talked about it in one of our previous series. When I mentioned, so in our previous series, we've talked about, when we actually want to discount future rewards for present one, and it is on top of that that we have this particular equation. So this discounted return equation is expressed as G of t equals R of t plus gamma R of t plus 1 plus gamma squared R of t plus 2 plus gamma 3 R of t plus 3 now plus dot dot dot, gamma raised by n R of t plus t plus n, right? Now, so that is the discounted return. Yeah. So we can more precisely write this as, let's say, G of t equals to the summation, K start from 0 of gamma raised by k, yeah, then R of t plus k. Yes. So this is, I think, a better way to express this equation where k stands from 1 to n, right? So yeah, that is basically that. So if we are going to be implementing this in for loop, so what we are going to say is, we are going to be implementing this in for loop. What we are going to say is simply G equals 0. Let's say for R in verse 1. Okay, so you're going to say G equals to, since gamma is a constant, gamma dot r, uh, say r, sorry. Okay, like I was explaining earlier, first of the three equations we are going to be looking at is the discounted return, and the discounted return is expressed as I have written here, so which can be much more precisely written as you can see underneath. And then to implement this in Python code, so we use for loop to do that. So say r plus gamma times g. So that is the equation. So someone might want to ask, why are we reversing the rewards? So we are doing that because we want to start from the last up onto the first. Okay, so that is basically that. And then also, in choosing the value of our gamma, like I mentioned in our previous class, when we choose, a value that is, if we choose one, for example, then what that means is that all future rewards are equal. We are not discounting any future rewards. We are just saying, okay, all rewards are equal. All of them are the same because one, anything times one remains, right? So, which can cause problems, right? So, in that case, you are trying to choose a shorter discount factor, which is gamma. So, sometimes you might say, gamma could be 0.99. Now, if you choose 0.99, which is, very close to one, but not one, so we can say that is, that keeps future result relevant. But if we choose a shorter one, let's say 0.90, for example. So with that, we can we can uh, we can have shorter horizon, or you can have much more marginalized. I mean, we can have more short-sighted future results or marginalized future reward. So that's basically that. So the first equation we'll be looking at here is the discounted return, which I've just shown. Now, the second one we are going to be looking at is log probabilities. Now, if you remember clearly in our last session, we talked about the output probability, of, because in this case, you do not just want a static policy, because we discussed that our policy is what is a length parameters that makes the agent realize, what to do given a particular action, or what action to take given a particular state, right? So you say the policy of an action given a state. So we categorize that into, I think, two categories. We talked about the deterministic, and then we talked about the stochastic. So I mentioned that the deterministic approach is one whereby we already knew, like you are giving a specific, approach towards what the agent should do given a state. And then we said the stochastic is length. It's not just, given, it is length over time by exploring the environment. Now, talking about that, so in looking at the policy, right, for stochastic approach now, we have range of probabilities. So we talked about an example where I said, for example, a given agent that has two actions, two possible actions, left, let's say left and right. So let's say the probability of going left was, let's say, 30%, and probability of going right is, let's say, 70%. So given a particular state, okay, given a particular state, you know, given a particular state, so it definitely wants to go for the one with the higher percentage. So this is a log probability. The probability of, going right given a particular state based on the length value policy, based on the length policy, value policy, is 70% for that given state. So it's going right in that case. And this is length. So when talking about those output probabilities, if we want to increase the probability of good action, for example, now if probability is 0.01, okay, so let's say probability is very tiny, 0.01. So in that case, it makes tiny changes to the weight of the length parameters. It makes very little gradient updates on the weight. Now, so in that case, we do not want to just use static probability. So what we want to use is log probability. Okay, we want to use log probability. So in that case, we say the log probability is what we are going to use. And in doing that, you can say that the gradient of log probability of a given policy, that is action to be taken given a state, right, is equal to the gradient of a given policy of an action given a state divided by the policy of an action given a state. I don't know if you get this. So this is trying to tell us that the gradient of the log probability of an action given a state is equal to the normalized gradient, is equal to the normalized value policy. Okay, is equal to the normalized value policy. So in this case, you are just normalizing the value policy. And with that, we can have a much more uniform, a much more scaled, probability of our value policy, that is, of an action given a state. That's the log probability of an action given a state. So it's much more scaled and much more normalized, or much more normalized. So in that case, you can say the gradient of the log probability of a value policy equals to the gradient of the policy divided by the value policy itself. In this case, we have a much more scaled output probability. So, and what this helps us to do is this. Now, if you have the value policy, if we have the value policy of, let's say, the policy of an action, given a state, okay, is equal to 0.001, right? So that is, this is the probability of that action. This is probably 1%. Okay. So meaning probably the agents encounter this particular state very rarely, and it has this probability of taking an action against the state, right? So now, so this is a real action, right? So here, if we apply log probability on this, so we say the log of 0.001, that is going to it's going to push the probability up strongly. It's going to push it up significantly because this is going to give us minus 6.9. Okay, this is going to give us minus 6.9. We calculate the log of 0.001. Now, so what happened here is that the gradient is large, okay, and then it pushes up the probability very strongly. So meaning even the most minute action is captured during this learning process, so that the agent is being able to capture every possible scenario within the environment. Okay, so and this helps to push out the probability significantly. So this pushes up probability significantly, right? So that is that. Right now, how about if we have a very large probability? Okay, what if we have very large probability? So let's say the probability of an action given a state equals to 0.99, right? 0.99. So the log probability of this, log probability of this, is close to zero because the probability of one is zero, right? So this one is very close to zero. So what this means is that the gradient is small. It barely changes when the agent is very confident. So this, I'll say, the gradient update is very small when the agent is very confident. So what that means is that it helps the agent. So this particular formula, log probability, helps the agent to really explore the environment and really keep its experience intact. For those that it is confident of the action to be taken given the state, it pushes very confident. It pushes the gradient very small. So there's no significant update that is happening. Because if it is not small, it means it is going to focus on those that it has learned and not really on those that it is yet to explore. So that is exactly what log probability helps us to do. For those that it is confident of the action to take given the state in its value policy, it keeps the gradient very small so that very little update happens there. But for those that it is yet to explore, the gradient pushes higher, okay, so that those ones are learned as well within its value policy. So this helps, with automatic scaling, which is what we need. So rare but good action, pushes harder, while common actions, barely need to be adjusted, right? So that's basically that. Okay, so now the third equation we are going to be looking at is the advantage. Equation 3 is the advantage. Okay, so this is equation 2. Now equation 3 is the advantage. Now, when we talk about advantage, what does it mean? Okay, so now the problem with raw returns, okay, when we calculate the entire return over a large amount of time steps, is that if an action, if a single action is taken, if a single action is taken, and if an action is taken, let me just say if an action is taken, and we got 80 returns, for that action, okay, can we say that is good? Well, that could be good depending on what the average of those return is. I don't know if that makes sense. So let's say in a series of time steps, or in a series of episodes, maybe in 5 episodes, for example, we have one of those episodes to have a return of 80, right? Now, when we get a return of 80, you know, for those time steps, or let's say, and we take, when the agent decides to take a particular action, that's it takes series of action, of course, over time, and it gets a particular return on the time steps. Now we got 80 as the return. Okay. Now, can we say that 80 is good? Like, can we say it's a good result? Can we say it's a good return? That will depend on what the other 4 returns are. If the 4 other returns are 500, 600, and then we are getting 80, then it means 80 is not so good enough. But if other returns are like 90 and 50 and so on, then we can say, okay, it is good because it is within range. Okay. So now, how do we measure the baseline? So let's say, like I mentioned, if um, so now it will be good enough if, let's say, we have 3 episodes. Episode 1 has G of, let's say, 90. We'll clean this. One as 2 as G of, let's say, 50, and 3 as G. Okay, so then here we have, so let's say we have just 3 episodes and G as 80. Now we'll say this is above baseline, right? So that's above average, right? Or average, right? That is above average. 90 is below average. Okay. Then you can say this is above average. Then we can say this is so well, this is above as well. But let's say this is below 2 because this is even 90. This is 80, sorry. Okay, so how do we measure baseline? So that's the question. How do we measure baseline? Okay, now we measure baseline, based on the advantage. So say the advantage of a given action, given a state, is uh is the actual return Q state and action minus, the expected return of the state. So say A is how much better or worse than expected. So say A of Q comma S, sorry, S comma A. So when we are writing a value policy, the way we write value policy is this, or A given S. But when we are writing this formula, so it's going to be something like S comma A, state departure. So where this is the expected, so like how much better or worse do we expect? Okay. YQ S comma A. Q of S comma A is the actual return when taking action in a state. Okay. The actual return that we are getting when taking an action in a state. So yes, that's the actual return when taking action in a state. So while V of S, so you say V of S, is the expected return from states. So V of S is the expected return, from a given state. So how do we do this? How do we solve this? So we say in practice, we approximate, with one step, you know, we approximate with one step. So in doing that, we say A of S comma A, okay, approximately to B R, which is the return, plus gamma, which is the discount factor, dot V of S comma A, sorry, V of S prime, which is the future state, minus V of S. So which is the expected return from a given state. So this is the expected return from the future state. So in this case, the expected return, which is A of S comma A, is the reward plus the discounting of the expected reward from the future state minus the expected reward of that given state. Okay, so that is basically that. So with that now, so now let's say, for example, you have a baseline. We have a baseline, expected return, okay, from a given state. That's V of S. We have it to be, let's say, 55, right? Now, if action zero is taken, the return is going to be A. A equals return would be, let me change this. Colon here. Colon beta is better calculated. A equals to 45. 45 minus 55 is going to give us 10. Now, if return is 45, oh, if return equals to 45, then A equals to 55 minus 45. That will give us 10, right? So now this is being this is being predicted. So there's another approach in reinforcement learning that we call the actor critic approach. So we call it the actor critic approach. So this will be predicted by the critic. Okay. Now, so let's say action one is being taken. So here the return is 80. Then the action is going to be what? Action is going to be 55 minus 80, which is going to give us what? 25. Let's say action 2 is being taken on. Return is actually 95. Then you can say action equals to 55 minus 95. And that's going to give us 55 minus 95 is what? Will give us 40. So you can say this is worse because this is minus 10. Oh. 45 minus 55. No, no, no. It's 45 minus 55. So it's supposed to be return minus V of S. So this should be 45. It should be 45 minus 55. Why this should be 80 minus 55. And then this should be 90. I'm sorry, 95 minus 25. So it's going to be minus 10, it's going to be 25, it's going to be 40. So this is going to be worse. It's going to be better. And this is going to be good. So because the advantage is going to help us to be able to calculate the expected return. If the critic is telling us this is what we are getting, okay, as a reward, and then the value policy, so I'm sorry, the expected return, the baseline expected return, is telling us this is what we are getting. We can be able to find the difference and know what advantage we have. The higher the advantage, the better it is for us to be sure that this is what the expected return, that with this particular action, we can get a better expected return. So that is that. Now, lastly, what we are going to be looking at is policy gradient. policy gradient. Okay, we'll be looking at policy gradients. Now, so what is policy gradient? So policy gradient helps us to combine all of these things together. So in policy gradient, you can calculate the loss to be equal to summation, log of the value policy of A of t given S of t times G of t, right? Now, so what this means is that for each action taken, we multiply it by the log probability, multiply its log probability, which is this. We multiply it by the expected return. Okay? We multiply the log probability by the expected return it produced. And then we sum all of them up. Okay? Now, so we have a negative sign here. Now, what the negative sign is should will help us to do is that we want to maximize the reward. Okay? And then we optimize loss as well. So why the optimizers, they minimize the loss. Now, so negating the reward means we are minimizing the problem. Okay, we are minimizing problem. And then with advantage, what that would look like is minus summation of log pi of at given st times et. Okay, so that is basically how that will work. So here we are trying, we are not just looking at the log probability alone. Now we are also looking at it by multiplying, by also keeping in account the return and then the advantage. So we multiply it with the return, and then whatever it is it gives us, we add, we also multiply it by minus, such that we can minimize the reward. I'm sorry, we can maximize the reward, sorry. We can maximize the reward, and then the optimizers that we are going to be using, we help to minimize the loss. We will minimize the loss. That will be done, while we are writing our code. So now just take it, try to, keep in mind these three equations. They are very important. So, and while this is going to be referred to as the actor-critic approach. So now we'll go into code now. Now, the first thing we are going to look at, when writing our code, like I've always said, is we are going to import the required libraries. We import the required libraries. So here, we are going to define a function that helps to plot the discounted rewards. So here is a function that helps us to plot the discounted rewards. So if you look at this clearly, you realize that we have the three different versions of the gamma. We have, okay, color label, and then label for each of them. So you mentioned that this 0.99 is the standard, 0.95, and then this is short-sighted because it's, far lesser, and this, is higher. Sorry, it's lesser, compared to 0.99. But 0.99 is not one. It just sits at a sweet spot where it helps us to, discount future rewards. And then we can iterate over that, then calculate our weights, you know. Yeah, calculate our weight, and then we plot the required graphs. Hmm? Okay, so we have steps here, 0 to 51, that's 0 to 50. Yes. Okay, so you can calculate the weight by multiplying our gamma, by each of the values over there, and then we get the weights. Whatever it is that we get here, we plot our graphs. So you don't need to even print this. I just rule this. So now let's take a look at what that would look like. So you can plot discount factor. Okay, so let's plot this graph. So so here you can see where we have 0.99, you can see this is, moving steadily. So you can see it's moving steadily. So for 0.95, you can see how sharply it was. 0.90, it's far less, So it's very steep, into future rewards. I mean, into future time steps. So you don't want something that is so steep like this. You want something that is, that's far much more, better like this. So with this, we'll prefer something like 0.99. If you had done one, so it would have just been a straight line, but we prefer something, 0.99 that can, steep down into future as this. So that's the reason why we are choosing that value. Okay, so that's that. Now, the next thing we want to look at is to plot return calculation. So here we have the plot return calculation. You can see the gamma. We've now, decided, I mean, we've agreed. We can agree from the previous graph that what do you call it, 0.99 is the best return that we can choose for this task. Now here, we assume that these are rewards, then n is the number of rewards that we have. Okay, so 1, 2, 3, 4, 5, 6, 6. Now, so we are running a for loop to calculate our G. I told us, how we calculate the G earlier. So we'll be calculating our G. So here we have G equals 0, return equals this. So you can calculate the G as, R from the rewards plus gamma, which is 0.99 times G. Initially, we initialize G to be 0. So it's going to be increasing, and then we are going to keep calculating our future um, rewards. Okay? And then we insert this inside what do you call it, inside the list as well. So whatever it is that we're able to get from the G and the return, then we use it to plot a graph. So here you can see two different graphs. The first one is plotting, the number of time steps on the x-axis, and then we have the reward on the y-axis, right? So you have x time steps on x, and then rewards on y-axis. So while the second graph is plotting the time steps as well and the rewards. But in this case, um, okay, so this plotting is from the end. So these are discounted reward from the end. So why this is plotting it, per time steps. This plot like this calculating the time the reward backwards. So why this is just per time step. So we'll see what each of them is going to give us. So call this function print it. So we call this plots return calculation. So now with this, you can be able to see what the reward was like, for each given time steps from 0 to minus 100. By each time step, so it was on the fifth time step that we were able to have this. But when we plotted it backwards, so you can see that at each time steps, we're able to accumulate rewards over time by each time steps, and then we can see them this way. So this is to tell us that it's better for us to compute our discounted time steps by calculating it backwards from end. So that is that, which I also explained during the mathematical intuition. Now, the next thing we are going to be looking at here is log probability intuition. So which we are going to also plot a graph for. Now, so here we have, a number of equally spaced numbers, mean space, okay, 0 to 0.01 to 301 difference. So here, that's that. Then also, we're able to calculate the log probability of these numbers, right? Now we are going to plot a graph of probes against log probes. Okay. Then after doing that, we're also going to, okay, here we are going to have a scatter plot where we are able to annotate, key points. So let's take a look at that. So we plot this, we call this function, invoke the function. Okay, so here is the log probability. So you can see starting from 0 up until 1. So you can see where the predicted output is 0.1. You have log of minus 2.3. So here the agent is not so sure of the action taken at that point. So you can see the log probability increased it, and that will help to largely update the gradient. So here we have 0.5, which is not very short too, but I mean much more significant. So you can see here still a bit higher, 0.69. Then here where the agent is much more short, 0.9. So you can see it has very little, update. So what that is telling us is, the log probability gets smaller as the agent tends to give a much more confident, probability on the action taken given a particular state. That is how that is.